Today, you get to witness an experiment that proves there's more to electricity than what you've been told. We are taught that if we want more electricity to come out of a generator, we must put more work into that generator, into turning it. But what if that wasn't true? What if we could do less work and get more out? For hundreds of years, universities, they've told us in physics textbooks and electrical engineering courses, that's not possible. You must put more energy into turning that generator if you want to get more electricity out. But today, with a simple setup using off-the-shelf components in a matter of minutes, we are going to contradict centuries of university facts and electrical engineering bottom line. After which, we'll jump into an update on our pulse motor generator, the project in which we have been working so diligently towards the end goal of producing excess electricity from the open, abundant system with which we are a part of. But first, let's get into this experiment. A motor, a generator, what's the difference? What do they do? Electricity in to a motor, out comes kinetic energy. A generator, kinetic energy goes in, motion, and out comes electricity. That's it. How is this achieved? It's achieved with wires in the form of coils, so they coil wire, and magnets. A motor puts electricity into these coils of wire, and it produces motion. It repels or attracts because of the electromagnet created in the coil of wire with electricity flowing through it, repels or attracts the rotor with the magnets on it. In a generator, it's the opposite. We turn the rotor with the magnets on it, and the magnets moving past these coils of wire cause electricity to flow out. A motor and generator, they're two sides of the same coin. In fact, so much so that when a motor operates, as soon as you start to press the pedal on your electric vehicle and move forward, simultaneously it's acting like a generator. This generator, if the energy is going in this way from us, the generator action starts to generate electricity out the opposite way. It's a force, a contradicting force. This is called back EMF. And the generator doesn't get away from it either. The generator, as soon as we start producing electricity by turning the rotor, it gets harder and harder and harder. It wants to act in the opposite direction. So a generator acts like a motor acts like a generator. There's back EMF. The back EMF is a tax that's unavoidable. So they tell us. The back EMF, we have to pay the price. There's a huge amount of engineering that goes into motors and generators to negate or deal with the back EMF. Motors usually create heat with it, generators as well. It's the reason why a generator, if we want more out, we have to put more in. You have to turn it harder. It gets harder and harder the more electricity that comes out because it acts more and more like a motor in the opposite direction. Likewise, the reason we need to keep pressing on the accelerator in your electric vehicle to go faster and faster is because there's more back EMF created. It gets harder and harder and harder to go faster. You need to put more electricity into a motor to go faster. You need to put more kinetic energy into a generator to produce more electricity out. End of story. Let's think of our load or the output of a generator as a little man. So we've got a little man down there and there's zero work here, and if he goes down to this end, maximum work. So more work out as he moves along this distance. But back EMF comes into play. Back EMF is a hill, and it gets steeper and steeper and steeper. The more work you want to do, the steeper the hill is this load or the output has to climb up. Let's keep that in mind. The harder the prime mover needs to spin that generator, work to spin that generator. What is a prime mover? Well, a prime mover is the primary means in which we turn a generator. Could be wind, could be gasoline engine, a diesel engine, hydroelectric dam, a river flowing with a turbine in it, all examples of a prime mover. Turning the generator to produce electricity or the load, that little guy moving up the hill on the other page. Today, for our experimental purposes here, we're going to use a DC motor. So I got a DC motor, that's our prime mover, and our generator is going to be this little guy here. This is called a stepper motor. So a stepper motor has two sets of coils. It's actually a pulse motor, very similar to the build that we're currently doing on our big one, and the Bedini motor. It has two sets of coils, and when you want the rotor to turn, you put a pulse of energy through one set. It causes the rotor to turn from one pole or magnetic pole to the next, so from a north to a south. That's one increment, one step. If you want it to do the next step, you put a pulse through the other set of coils, and again, it turns one step. The number of pulses you put in denotes and correlates directly to the number of steps that take place on the rotor, the rotation that takes place on the rotor. So this is used in robotics and industry everywhere for us to be able to tell the distance something has traveled, the amount of rotation that's happened. There's a robotic arm on an assembly line and you want it to move this far, you put a certain amount of pulses into the stepper motor that controls it. That's how it's achieved. But like we talked about, a motor is a generator and a generator is a motor. Some would require some upgrades in order to use it as the other, but this particular motor, we can just spin the shaft with the prime mover and it becomes a generator. It's going to produce electricity. That's what we're doing here. This is our prime mover, this is our generator, the stepper motor that we're turning with the prime mover. Our power supply here, you can see the amount of wattage or the energy required to turn the stepper motor. This is the load, and then this will give us an amperage reading on the load, how much power we're producing, and then the voltage. Let's turn on our prime mover, get a baseline. So you can see our prime mover it requires roughly 11 watts just to turn it on its own. That's without the generator, the stepper motor hooked up. So let's take our coupling here, we're gonna secure the coupling, and then let's try that again. It's roughly 46. We'll call it 46 watts to power the system. The prime mover took 11, so that means 35 watts is required to turn the generator. Get a baseline RPM reading here with our tachometer. 4,400, roughly 4,430 RPM. Obviously no amperage on the output. The coils are disconnected. This is a no load situation. Let's take a traditional load here. So these are resistors. What do we expect is going to happen when we connect this to one of the coils? Well, it's going to bog down. It'll take more electricity to turn this generator because now we're putting it under load. There you go. You can hear the RPM has decreased, 4260. We are taking 59 watts of electricity to power these resistors, which are starting to smoke because we're producing so much heat. Let's get those off of there. Exactly what we would expect in a traditional setup. What we're taught in school will happen when you load a generator. It takes more energy from the prime mover to turn it. But let's try the LED load here. What's going to happen? Is it going to be the same thing? Let's see. Okay, now we're producing electricity on the output. You can see it's taking 1.2 amps, producing 1.2 amps and approximately 3.4 volts. So we've got 3 or 4 watts of electricity being produced from the generator, and our input wattage to our prime mover has decreased substantially. We're down from 46 to 38.8 watts. The RPM has also increased by over 100 RPM. We still have one coil that's unused, an open coil. So let's short out that coil. It's going from a no load situation to a short. What just happened? Well, we're still producing electricity on the output, approximately the same amount. We're now at 1.27 amps, 3.3 volts. The lights are lit up. The second coil is now being shorted out. It's producing electricity as well. It's just turning it into heat inside the coil on the generator. So that's heating up. But look at what's happened to the wattage on the input. We've gone from 46 watts required to turn this prime mover and the generator down to 25. Our RPM now is at 4,750 RPM. So we're increasing RPM, we're decreasing the amount of energy required to turn the prime mover, and we're producing electricity. One final step, let's get rid of the LED load, and we will short out the second coil. Oh, I lost the first coil there. So there's the first coil. We're down from 46 to 33 watts, and if we short out the second coil, we are down all the way to 21 watts. 4840 with both coils shorted, 4850. What just happened there, everyone? Well, we saw that you can put less energy into the prime mover while producing more work on the output. We went from 0 on the output to 4 watts of LEDs plus all the internal resistance and work being done to generate heat on the second coil when we shorted it out. Our prime mover, we saw when we didn't have the generator hooked up, it required approximately 11 watts of energy just to turn the prime mover. Our system, starting out in a no-load situation, had 46 watts. That means the generator took roughly 35 watts of energy to turn it. With a no-load situation, no energy being produced. Then we shorted out one of the coils through the LEDs. When we did this, we showed that we were producing 3 to 4 watts of electricity on the output what happened? Our overall system dropped down to 38 watts of energy required to turn it. We've gone from 35 watts down to 27 watts required to turn the generator. We're producing 3 to 4 watts on the output, on the load. Then we shorted out the next coil. We shorted out the second coil. We went from 38 watts down to 26 watts. So now 26 minus 11, we're down to 15 watts that it's taking to turn that generator. And now we're doing work in that second coil as heat going through the coil, heating up the generator. We didn't power an LED load with it. We just wanted to show you that. If we shorted out both of the coils, we went all the way down to 21 watts, actually a little bit less. That means we were down to 10 watts of electricity required to turn that generator while producing heat and doing work on the output. That's like a 50 to 70% reduction in the energy required for this prime mover to turn this generator. And we're doing work on the output. That contradicts what I was taught in school as an electrical engineering student, as a physics student. I don't know about you, but some people will try and explain this as an armature reaction, which is an effect that's noticed in generators when you put them under load. Sometimes they speed up slightly, but do you get a 50 to 70% reduction in the energy required to turn the prime mover with an armature reaction, a standard armature reaction? I don't think so. So what's going on here? How is this explained? Well, let's remember our little stick figure here. This is our load, the amount of energy we're producing. Oh man, his eyes are out. The amount of energy we're producing is our stick figure. And remember before, we know that in order to do more work, he has to walk up a steeper hill. But we just demonstrated that that's no longer the case. There are ways of doing more work on the output, but you negate the hill. The back EMF, we're negating that. You don't need to climb up the steep hill, if at all. In fact, you might be able to go downhill and produce work. How is this possible? Well, normally let's call this, this is his shadow. So the red is his shadow. Work, the output, the load that we're doing, and has a shadow, which is amperage. This amperage is the flow in the wires, and normally it's in sync with the load. They walk very closely together, they're in sync. What happened here though, is we took the amperage and we made it lag the load. So now the amperage is back here. Normally the shadow is in tight proximity with the load, they're in sync. We pushed the amperage back, so it's out of phase with the load because of the way the coils work with the capacitance and the inductance of them. They squeezed off the amperage, they didn't allow it to flow. They squeeze off the amperage and they delay it from the load. So it's out of sync. The amperage is behind it, and what this does is that when the amperage is allowed to flow, it adds kinetic energy to the wheel instead of taking away from it. If it's in sync with the load, it's going to take away kinetic energy from the load. That's traditional back EMF. It's a negative effect on kinetic energy. You are doing negative work on the rotor with back EMF. If you delay the amperage from the load, you can do positive work on the rotor, adding positive kinetic energy while doing work on the output. That's what's happening here. And again, this isn't optimized. We're using off-the-shelf $20 Amazon stepper motors, just basic components. We haven't optimized anything. If you optimize the capacitance of the coils, the inductance of the coils, again, that's frequency dependent. But if you optimize that and you optimize the loads you're putting on it to keep everything at maximum efficiency, I mean, we just went 50 to 70% reductions. Imagine if you optimize the system, added some more coils. Is it possible to get 100% reduction? Probably not, right? They tell us that, but the same people that tell you that just told you that you have to do back EMF in order to get more work on the output. So, I don't know. Maybe not. It's interesting though. It's kind of like playing chess your whole life with one strategy. You get the same results over and over and over. You move the pieces in the same manner over and over. And then one day, you try a different strategy. Same pieces, just arranged in a slightly different manner, and you get a completely different result. We could have also come into this knowing that the generator is going to bog down. It's going to require more energy to get electricity out. We know that to be true, and we're going to look for supporting evidence for that bias. And we got that evidence. We tried a load initially. Could have stopped there and said, you know, everything, we got the evidence, exactly what we thought would happen, happened. But instead, we kept going. We tried a different load with a different impedance, and we got a completely different result. So do not stop, don't give up, don't come into something with one mindset and look for evidence to support it. What you think initially or what you want to happen, try and think the opposite and look for evidence to support that. Think from both sides, okay? Just keep an open mind, keep trying, never give up. You could be one shovelful away from the gold, and if you stop, you're never gonna get it. Losers stop. You're not a loser. You keep going. People who tell you stuff is impossible are losers. Don't talk to them. Get them out of your life. Just stay focused, build. Theory's all right, math is okay, but applied science is the real cherry on top. That's what you want. Applied science first, math and theory later. That being said, where are we at with our current build and not giving up? We had this area here all cleared out for the machine, all organized, the machine's on that end, battery banks here, everything's neat and tidy, perfect. The shop's opened up, a lot more room. And we're going to implement the high voltage supply. Our current boards are limited at 24, 36 volts just because of the DC to DC converters. So we have to have another step down transformer or DC to DC buck converter coming into it, which Joe built a beautiful one. And we implemented it. We turned on the machine, everything went wrong. The trigger signal wasn't working, things were firing, couldn't figure out what was going on. Obviously we thought it was the high voltage supply we implemented because that was the one variable we changed. Don't implement multiple variables at once, try one thing at a time so then you can troubleshoot and you know where the issues are coming from. Couldn't figure out what was going on. Eventually we realized there's a huge amount of electromagnetic interference coming in from this wall. Turns out the power supply for this building is on the outside of this wall. So there's a 5 volt, 60 hertz signal coming in through this wall in this area. When you have a 5 volt trigger signal on your machine, that's a big deal. EMI coming through the wall was causing all sorts of issues. It was going into the wires, false triggering, it took us a while to figure that one out. So we moved everything from this end of the shop down to that end, got everything organized. Now it sits in that area. There's no EMI coming in through the wall. The 5 volt signal's gone. So we got that solved. Still things were going wrong. Things weren't working. The high voltage supply was faulty. There was some issues with it. It was causing false triggering. We figured that out. We got rid of the high voltage supply. We're like, okay, let's just try and get the pulse width modulation. Joe built a beautiful board. It's all computer controlled wirelessly. We can modulate the duty cycle, advance and retard the trigger position. Perfect. We power that on, MOSFETs start blowing up, things are going wrong. It's putting out a constant 5 volts, which if you power these MOSFETs at 5 volts constantly, they'll start to smoke out very quickly. It's too much for them. Turns out there was a faulty pull-down transistor on the timing board. So again, we just had issues everywhere. Just the one weekend, we had 20 hours of troubleshooting into this system, figuring everything out, the EMI through the wall, timing issues with the high voltage supply, timing issues with the faulty timing module, and you can see how Joe and I work together because he's 2,000 kilometers away from my location, so we have to do everything remotely. There's a 3-hour time delay. It's a lot of work. And just know that even if a video doesn't come out for 4 to 5 weeks like this one took, we're working relentlessly and behind the scenes. Both of us have full-time jobs. We work an additional 20 to 40 hours, like 20 absolute minimum per week on this project. So know that it's coming out. We're working very hard on it. Your donations, thank you so much, go to the shipping cost. It costs a couple $100 just to ship components one way. We do that multiple times a week. All of the electronics that you see up here on top of the machine, this has all been donated from our main anonymous donor. So thank you so much for making that happen. They're good problems. They're teaching us something. There's no such thing as a bad problem. It's an issue that you need to be shown. You got to figure it out. It's a test, right? You're learning something from it. It's being shown to you for a reason. So learn from it. Keep that in mind. Problems are good. Something we've learned from this, and obviously we were already expecting this not to be just a whole shot to over Unity, just boom, boom, perfect self-running machine. We knew there was going to be issues going up to these high voltages. We wanted to have a lot of boards on hand, and that's what we have in the future. These first boards Joe produced, he did it all hand soldering, and what we realized, one of the issues he was having is that he was hand soldering. The temperatures of the soldering iron were too hot. They were causing failures in the gate drivers, but not enough that you could see. It shows up once we start running them. They're just not perfect. There's little faulty things. They don't trigger fully. anyways, going forward, we're now moving to Joe having a hot plate so that he can put the PCB board on there and it just solders itself with low temperature solder. Everything's uniform and even. That'll solve that issue. We're gonna do a run of 10 right now so that we have 10 of the V1.5. These current boards are version 1. We've got version 1.5 already designed. The PCBs are out. And yes, the schematic and the bill of materials is in the video description. Open sourced to you. Use as you will. Version 1.5 goes up to 90 volts with the DC to DC converters on there. Version 2, which we're now testing, Joe's testing higher voltages, will go up to 120, 150 volts. Version 1.5 boards are also being produced by our friend Fred in Hong Kong. Thank you, Fred. He's winding all the coils for us as well. He's producing 16 Fuller wound coils for us for the power coils, all uniform, exactly the same. We should have those in December. He's producing 12 generator coils. So just like this one, he's producing 12 of these. I've got the pellets in this one. I'll show you the footage there of me pouring the epoxy into the core here and getting the iron pellets in there. But he's producing 12 gen coils for us, 3 different gauges of wire, 0.2 millimeter, 0.45 millimeter, and 0.74 millimeter. 4 of each. So we've got different gauges. We can experiment with them, see the different results, see what we like. People will tell you that, oh, why would you put generator coils on a machine like this? You're not going to get more out than you put in. All the losses are just going to negate anything that you get out as gains. It's like, okay, well, so you say, but I just showed you in the demonstration today that we can negate back EMF. It's just rearranging the components in a different manner, using them in a different way. So you can go ahead and believe that you're not going to get excess energy by putting gen coils on there, but we're going to negate back EMF and the losses and generate power with these gen coils. Thank you so much, Fred. I am so excited not to have to wind coils by hand. You guys saw in the previous video how much work that is. Fred's also producing the version 1.5 boards. His factory is capable of cranking out hundreds of boards at a time. So once we get his process verified, then we'll switch over. He's going to produce like 30 boards for us at once. The gist of it being that we're going to have a huge amount of boards on hand. So then when we do blow stuff up, stepping up the voltages, it's not such a big deal. It doesn't set us back weeks and weeks and weeks. We can just implement fresh boards. Everything's uniform. Amazing. So we have 2 parallel streams going. Joe manufacturing boards in Ontario, Canada, Fred in Hong Kong. Once Fred's fired up and going, then Joe won't have to build the boards anymore. But for now, that's what we're doing. Moving forward, we're going to go into the high voltage extended run times next week. Joe has all the high voltage supply figured out. He's also got a beautiful battery flip-flop built, so it allows us to flip between the run and the charge battery. So the charge becomes the run becomes the charge. Every 3 minutes or so allows us to use up the excess energy from the charge battery and run the machine with it. Our hypothesis is that excess energy is coming into these batteries, the charge battery bank, because of the collapsing flyback voltage. It's a similar phenomenon to the back EMF that we described in generators and motors. The flyback is the collapsing magnetic field that flows in the back direction, the opposite direction of the energy it went in. So it flows back out of the coils as the magnetic field collapses. We're capturing this collapsing magnetic field and we're putting it into the charge battery bank. I'll get into the theory a bit more in the next video. I've talked about it in a previous video. This high voltage spike creates a dipole within the electrochemistry of the batteries between the ions and the electrons, and possibly other flows. There's all sorts of other flows of energy outside of the conductor that aren't electron based. So displacement currents, things like that. We'll talk about that in the next video. Thane Hines, he's the one that made me aware of this type of positive kinetic energy being available on a generator. We're moving forward with high voltage extended run times. We're going to start stepping it up to 36, 48, 60 volts, 72. We will do extended run times with the battery flip-flop, do a 10-hour run period, measure everything with our benchtop multimeter on top, so that allows us to do 5 decimal data logging of the voltages and the amperages. Those data loggers will allow us to monitor the amperage and the voltage in both battery banks, the conventional energy in between the 2 battery banks. To actually measure the potential energy in the battery banks, we'll have to use a Coulomb meter. But overall, just the extended run times and being able to show that the voltages are staying the same after the batteries have settled, things like that. Same amount of potential energy. We've done all this work definitively. This is an excess energy machine. It is a self-running machine that can produce excess energy. And that's about as good as we're going to be able to do on YouTube. There's no way of proving over unity through video or picture. But if we allow you to go out and do the same demos yourself by purchasing the boards that we have, building them yourselves. Again, all the files are open sourced in the description. Go nuts, do what you will with them, build your own machines, their own devices. That's really the only way you're ever going to truly know Over Unity exists, is by building it and implementing it yourself. Thank you so much to everyone for your support. It means the world to us. Your donations make this possible. If you can donate, the donation page, the GoFundMe is still up. Thank you to our main anonymous donor. We appreciate you. We both know where this is going. Thank you to Joe for the electronics, Kyle for the CAD, my YouTube guru in California helping me with the thumbnails and all the pointers on the YouTube videos. Thank you all so much for supporting this open source project, this collaboration. Stay tuned. We're going to get a new video out to you very soon. I love you all. See you soon.